Good morning, everyone. In today's lecture, we are going to learn about sequence labeling for part of speech and named entities. My name is Arghya Kundu, and my email ID is arghyak@yorku.ca. If you have any questions regarding machine learning, deep learning, or any NLP tasks, please feel free to drop me an email. So let's get started. So today, firstly, we're going to talk about parts of speech tagging, and then we're going to continue with the named entity recognition. In short, we call this NER. So let's introduce the task of part of speech tagging. So Thrax of Alexandria in 100 BC, or perhaps someone else, it was a long time ago. Anyway, wrote a grammatical sketch of Greek that summarized the linguistic knowledge of his day. This work is the source of an astonishing proportion of modern linguistic vocabulary, including the words syntax, clitic, and analogy. Also included are a description of 8 parts of speech, that is noun, verb, pronoun, preposition, adverb, conjugation, particle, and article. Although earlier scholars, including Aristotle as well as Stoics, had their own lists of parts of speech, but it was Thrax's set of 8 that became the basis for description of European languages for the next 2000 years. The durability of parts of speech through 2 millennia speaks to their centrality in models of human language. Proper names are another important and anciently studied linguistic category. While parts of speech are generally assigned to individual words or morphemes, a proper name is often an entire multi-word phrase, like the name Marie Curie, the location New York City, or the organization Stanford University. We will use the term named entity for, roughly speaking, anything that can be referred to with a proper name, that is a person, a location, or an organization. Although we will see the term in commonly extended to include things that aren't entities per se. Let's talk about some parts of speech. While these word classes do have semantic tendencies, adjectives, for example, often describes properties and nouns, for example, people. Parts of speech are defined instead based on their grammatical relationship with neighboring words or the morphological properties about their affixes. Parts of speech fall into 2 broad categories: closed class and the open class. Closed classes are those with relatively fixed membership, such as prepositions. New prepositions are rarely coined. By contrast, nouns and verbs are open classes. New nouns and verbs like iPhone or to fax are continuously being created or borrowed. Closed classes words are generally function words like of, it, and, or you, which tend to be very short, occur frequently, and often have struggling uses in grammar. 4 major open classes occur in the languages of the world: nouns, including pronouns, verbs, adjectives, and adverbs, as well as the smaller open classes of interjections. English has all 5, although not every language does. Nouns are words for people, places, or things, but include others as well. Common nouns include concrete terms like cat and mango, abstractions like algorithm and beauty, and verb-like terms like pacing, as in his pacing to and fro from became quite annoying. Verbs refer to actions and processes, including open class main verbs like draw, provide, and go, and closed class auxiliary verbs like can, will, had. Auxiliary verbs can mark semantic features of a main verb, such as its tense, aspect, or made. Adjectives are often describe properties or qualities of nouns, like color, that is white or black, age, old or young, and value, good or bad. Other closed classes or function words include pronouns, which act as a shorthand for referring to an entity or event, or conjugations that join two phrases, clauses, or sentences, including coordinating conjunctions like and, or, and but, or subordinating conjunctions like that, in I thought that you might like some milk. In this sentence, that links the verb thought with the clause you might like some milk. Part of speech tagging is the process of assigning a part of speech to each word in a text. Tagging is an ambiguous task, but words are ambiguous. They have more than one possible parts of speech, and the goal is to find the correct tag for the situation. For example, book can be a verb, book that flight, or a noun, hand me that book. Here's a sketch of the parts of speech tagging. The input is a sequence x1, x2 to xn of tokenized words and a tag set. And the output is a sequence of y1, y2 to yn of tags. Each output yi corresponding to exactly to the one input xi. The accuracy of part of speech tagging algorithms is extremely high. One study found accuracies over 97% across 15 languages from the universal dependency tree bank. Accuracies are on various English tree banks are also 97%. This 97% number is also about the human performance on this task, at least for English. So the universal dependencies Tagset, this is a snippet of that. As you can see, the examples and the descriptions of the tags are provided here. You can refer this for future endeavors if you want to create any post tagging models. Here are some sample tag sentences. Notice that we have to make decisions about segmentation. Punctuation or the English is often segmented off as a particular. And the same word can have different tags in different sentences. So part of speech tagging is useful for NLP tasks, most notably for parsing, where it has long played a part, but also for machine translation, sentiment analysis, or even text-to-speech systems. For example, lead is pronounced lead when it is a noun, but lead when it is a verb, or object is pronounced object when it is a noun, but object when it is a verb. Tagging is also important for linguistic or language analytic computational tasks, like studying the creation of a new words or measuring meaningful similarity or differences. Now, how hard is pause tagging? In English, only 15% of word tags are ambiguous. So 85% of words don't need any disambiguity. For example, Janet is always a proper noun. Hesitantly is always an adverb. But those 15% ambiguous words tend to be common words. And so they occur far more than 15% of the time. Indeed, around 60% of word tokens in a running text are ambiguous. For example, the word back can have more one of 5 parts of speech tags, as shown in this slide. For example, the first is an adjective, the second is a noun, the third is a verb, and then the last is a adjective again. So how accurate are modern pause taggers? In fact, they're quite accurate, for English at least, and for a few other languages also, where we have sufficient hand-labeled training data and which have sufficient simple morphology. Tagging is mostly solved a problem, is a mostly solved problem. The accuracy, that is the percentage of tokens that the tagger assigns the correct tag to, is about 97%. Of course, for English, the baseline itself is quite high. What's called the most frequent class baseline is simply the tag every word with its most frequent tag. For unknown words, tag them as nouns. The baseline gets around 92% accuracy. Simply because, as we have seen, many words are not ambiguous. Part of speech taggers generally make use of 3 sources of information. Let's consider disambiguating the words in the sentence, Janet will back the bill. One source is the prior probability of the word having that tag. So the word will is always an auxiliary. Less frequently a noun, like someone of strong will, or a verb. Another source is the neighboring words. The usually precedes adjectives and nouns, not verbs. And the final is the makeup of the word itself. The prefix "un" often indicates an adjective. The suffix "ly" almost always an adverb, and capitalization is a strong hint of word of proper nouns. Pause tagging can be done with classic supervised machine learning algorithms like hidden Markov models or conditional random fields, or with neural models. Either neural sequence models trained from scratch or large language models fine-tuned. For English, with sufficient training data, all achieve about equal performance. And all make use of the information sources we discussed. Hidden Markov models or conditional random fields by human-centric features, and the neural models by inducing these features via representation learning. We have sketched a high-level part of speech tags and the task of part of speech tagging. Let's now introduce the task of named entity recognition. Proper names are another important and anciently studied linguistic category. While parts of speech are generally assigned to individual words or morphemes, a proper name is often an entire multi-word phrase, like the name Mary Curie, the location New York City, or the organization Stanford University. Part of speech tagging can tell us that words like Janet, Stanford University, and Colorado are all proper nouns. Being a proper noun is a grammatical property of these words. But viewed from a semantic perspective, these proper nouns refer to different kinds of entities. For example, Janet is a person, Stanford University is an organization, and Colorado is a location. A named entity is, roughly speaking, anything that can be referred to with a proper name, a person, a location, and an organization. 4 entity tags are most commonly used. That is a PER for person, LOC for location, ORG for organization, and GPE for geopolitical entity. However, the term named entity is commonly extended to include things that aren't entities per se, including dates, times, and other kinds of temporal expressions, and even numerical expressions like prices. 4 entity tags are most common, as I said before. That is the PER for person, LOC for location, ORG for organization, and GPE for geopolitical entities. The task of named entity recognition finds spans of text that constitute proper names and tag the type of that entity. Here's a text showing some sampled named entity recognition output. You will see that in this text, 13 mentions of named entities are included, including 5 organizations, 4 locations, 2 times, 1 person, and 1 mention of money. Named entity tagging is a useful first step in lots of natural language understanding tasks. In sentiment analysis, we might want to know a customer's sentiment towards a particular entity. Entities are a useful first stage in question answering, or for linking text to information in structured knowledge sources like Wikipedia. And named entity tagging is also central to natural language understanding tasks of building semantic representations. Unlike part of speech tagging, where there is no segmentation problem, since each word gets one tag, the task of named entity recognition is to find and label spans of text, and is difficult partly because of the ambiguity of segmentation. We need to decide what's an entity and what isn't, and where the boundaries are. Indeed, most words in a text will not be named entities. Another difficulty is caused by type ambiguity. The name Washington can refer to the educator Broker T. Washington, or the sports team, the location, or the geopolitical entity. The standard approach to sequence labeling for a span recognition problem like NER is biotagging. This is a method that allows us to treat NER like a word-by-word sequence labeling task via tags that capture both the boundary and the named entity type. Consider the following sequence. So as you can see, this sentence has been properly tagged using the PER as a person, ORG for organization, and LOC for location. Here shows the same sentence represented by the biotagging. Notice that we have tags corresponding to person, organization, and location. And now we have one tag per token. But how does it work? In biotagging, we label any token that begins a span of interest with the label B. Tokens that occur inside a span are tagged with an I, and any token outside of any span of interest are labeled O. While there is only one O tag, we will have distinct B and I tags for each named entity class. The number of tags is thus 2n plus 1 tags, where n is the number of entity types. Biotagging has the advantage that we can represent the task in the same simple sequence modeling way as part of speech tagging, assigning a single label yi to each input word xi. There are variants of biotagging in which there is no B tag, or in which we add an N tag, or a single tag for single words. Like part of speech tagging, named entity recognition is done by supervised machine learning, where we have an human-labeled training set in which some text is marked up with named entity tags. We can use classic ML algorithms like hidden Markov models or CRF or neural models. We have now seen the idea of a named entity tagging, an important first step in many NLP algorithms.